All right, I think we'll go ahead and get started. Thanks everybody for coming. Welcome. I want to thank, as always, Jay Familietti and the Global Institute for Water Security for lending us staff to put this on. So thank you, Michelle, Mark, and others. And of course, John Pomeroy and Global Water Futures for underwriting this seminar series. We're very fortunate to have that connection and also to reach out to our partner universities in Ontario and across the globe through the simulcast version of this lecture. And of course, it's recorded on YouTube as well for others to watch. A reminder, next week we have Alex Konings coming from Stanford University. Jay will be hosting her while she's here, and I encourage you to come to the lecture. It'll be here in this room, same time. But today, it's a real pleasure to welcome András Bárdossy. He is a professor of hydrology and geohydrology at the University of Stuttgart. As many of you know, he is really a global thought leader in the area of stochastic modeling, geostatistics, stochastic surface and subsurface hydrology. András has really an interesting background. A first PhD in 1981 in mathematics from Budapest, and a second PhD in 1993, I think it was, yeah, from Karlsruhe with Eric Platt. And this has given him really a unique purchase on several of the key quantitative problems facing our field of hydrology. For this, he's received many awards. He was the recipient of the Henry Darcy Medal from the European Geosciences Union in 1996. He's a member of the scientific committee of the International Hydrology Program, the national program, and a member of the State or Senate Commission on Water of the German Science Foundation, the DFG. Importantly, he's also the editor-in-chief of Journal Hydrology and has been for about 10 years. He handles personally about 500 papers a year. Those are new submissions per year. So his efforts and contribution to our community have been enormous. I think what I've really appreciated about András, who I've known for 20 years probably, visited you about 10 years ago, is his passion for PhD advising. He's advised, I think, 47 PhD students. You'll know many of them. Amir Aga Kuchek at University of UC Irvine won AGU Hydrology Section Early Career Award last year. That was huge. He's had many postdocs that have gone on to great things. Erwin Zahi, for one, who's editor-in-chief of HES, a rival journal to Journal Hydrology. So it's really with great pleasure that we welcome András. He's here for the whole week, and if you've not had a chance to interact with him yet, he'll be here for a couple of more days. And thank you so much for coming to Saskatoon.
So, Jeff, thank you very much for this nice introduction. And it is a real pleasure for me to be here. It is, I know this is a very important institute here, and to see so many people interested in hydrology is, and not at a big conference somewhere, is a very unusual thing. I was thinking a lot about what to present today, and then finally I decided I had one presentation which was a little bit artistic, so very nice theoretical, another which was very, very technical. So I decided to go for the third, which is a little bit of both. So I'll speak about what is really our problem with hydrological modeling. And let's start with the following thing. The next appearance of the Halley's Comet is on the 28th of July, 2061. Bad news, because I won't see it. So it's very, very unlikely. But it shows that in certain parts of in science, we can do very exact predictions. But if I ask the question, when is the next flood on the Saskatchewan River, I don't think that we can answer this question with a similar accuracy. And what is the reason? Why are we just second-class scientists? And if we take an astronomer, will he do a better job? I hope not. And the problem is, of course, there are less stars than raindrops, and we are handling a very, very difficult to observe system. We cannot follow each individual raindrop and look what it does, because we cannot even observe it correctly. So we have this problem. We have models which are much less accurate. And why? Why do we have all this uncertainty? First of all, observations are a very important source for our models, but also a very important source for uncertainty. I'll concentrate a little bit on that. Then we have problems with how to describe the processes. There are still many parts of our processes which we do not describe in the really appropriate way, and parameters are uncertain, and very often we concentrate on this part. We try to, we know everything is somehow wrong, not fully wrong, but to some extent wrong, and then we play around with the model parameters and hope that everything will get better, and not on the reason, not why the things are wrong, is where we work on. So model parameters cannot compensate for the observation errors, and if they do so, then we have a big problem, because then we have a good model because of the wrong reasons. So we have to think about that, and one of our biggest problems is precipitation uncertainty. We usually observe precipitation at discrete locations with small devices, and then try to find out what happened in the area. Not only what happened in between, even the integral is difficult. And what you can show is that observations are not representative. One can show that under normal circumstances, it is so that for the really big precipitation events, about 2/3 of the cases is underestimated and 1/3 is overestimated. So it's not even symmetrical. So we have a very big problem here, and what we try to do is really that we try to calibrate, we smear the things, we smear all these errors to get something working reasonably well. And my question will be that can we do a little bit different thing? Can we find parameters which, instead of parameters, kind of combinations which work reasonably well? That's a typical case. If we measure precipitation, that is what a measurement network would bring, and what we want to know is what is behind it. And I don't think that you guessed it. But this is the typical problem. We do not know what is really there, and we have to work with that. We have to find some solution. Now, if we know that precipitation is a source of uncertainty, what do? We try to estimate better. We tried to put a lot of effort in estimating precipitation, and I did that for some British catchments, and the idea was the following. We have a lot of observations, and I take 30 observations in a catchment, say, and I take 10 of them randomly in 100 different configurations, and I always estimate the rest. And then there I can check what procedure is better and which is not. So it's a kind of split sampling approach, and I used 3 different methods: nearest neighbor, inverse distance, and ordinary kriging. Here, this table shows that nearest neighbor was never better from these hundreds configurations, never better than inverse distance or ordinary kriging, and ordinary kriging was in 71% of the cases better than inverse distance. Okay, that's good. We have a better technique. We have better rainfall. Let's hope our model will also perform better. But now we put this rainfall into a rainfall runoff model, and look what happens. And what happens is very interesting. Namely, what happens is suddenly the difference between the worst and the best is becoming very small. The performance, this is the Nash-Sutcliffe coefficient, and practically the error, if you standardize them, then it's only 3% worse than ordinary kriging, and inverse distance, which was better, becomes the worst. Does it mean that it is not worth to put so much effort in this thing? Yeah, and why is nearest neighbor suddenly so good? The problem is these two methods are smoothing. Nearest neighbor is not smoothing. It's keeping the variability. And not only the means, but the variability and the means are driving hydrology. So the good variability or the good mean do the same thing. But none of them is really good. So it is very likely that we should not only work on better precipitation estimation, but we should think about what kind of variability could precipitation have. What do the observations tell us? Okay, so the research question, which I'm trying to answer, is there a realistic realization of precipitation so that models perform well? Okay, so I have a model, and at this moment, I'm not changing the model, I'm changing the precipitation. But I'm changing the precipitation in a different way. I'll tell you what this means. A realistic precipitation, something what could have happened. Okay? That this means we kind of calibrate the precipitation. It sounds very strange. It's very absurd. But the main goal is to understand whether there is a contradiction in our system or not. So if my non-contradicting precipitation and a reasonable model fit well together, then it could be a good model. Yeah? So this is the main idea. This is a space-time problem. Inverse modeling is done very often in groundwater modeling. But then you take one field, for example, a hydraulic conductivity field, and try to estimate it from the hats. Here we have the problem that every day we have a field if we have a daily resolution. So it's a much bigger dimension, and we have a lot of constraints. So we would like to have fields which look like rain, and here I tell you what do I mean by realistic realization of precipitation. First thing, if I look at a precipitation map, what I obtain with the technique, it should match the data which were measured. So we have, at certain locations, we measured precipitation, and the generated field should honor that, because we believe that at least there were some information, and we should not just destroy this impure information. The second thing is we want to have a reasonable spatial variability. We do not want to have a mosaic where everything changes everywhere. but we have some kind of variability which we can measure with something like a variogram or some kind of covariance function. That is also interesting, and it should follow the distribution which we observed. We should not invent very high precipitation at locations which are between the stations. We should remain in a reasonable range. Okay, so these are the constraints. Now, I'm trying to apply this thing for two catchments, and more or less physically based model. It's a Sheetran model. It's the model from Newcastle. There is a She model by the DHI, so it's a partial differential equation based model. Daily resolution on the Tyne. Here you see the Tyne catchment. The Tyne is in North England, and Newcastle is somewhere here. And the model was set up by Liz Lewis, and it is a 2,176 square kilometer catchment, and I'm using 5 by 5 kilometer blocks. But the rainfall simulation is done on a 1 by 1 kilometer, and then it's upscaled. 10 years of daily discharge and 10 years of precipitation are available. The other catchment is near Stuttgart. It's on the Neckar. Ning Wang set up the model for me, and it's 1,100 square kilometers, 1 by 1 kilometer resolution, and 12 years of daily discharge. Okay, so that is available. Now, as a next thing, I would like to look, can I get a precipitation which works better, which fulfills the previous conditions? I could just generate precipitation realizations. In this case, we selected a cupola approach. If you don't know what cupolas are, it doesn't matter. It's a technique. It's a kind of technique here. We also looked at the zeros, and we set up a model which does the right covariance. So we can simulate realizations, and as a first step, we tried just randomly. So we generated every day a so-called conditional realization, which honored the points and was giving some reasonable variability in between. And then we compared what was the interpolated the model, what we had before, and how did the simulated things work. And what you see here, this is just a small part of the simulated series here. From the 1500 to 1550, just randomly selected on the Neckar, and the blue line is the observed discharge. The dashed lines here are different simulated ones, and what you see is there is quite a bit of difference between the two, but somehow, some of them are relatively close, but it's difficult. This is not a game, not a lottery. We will not just win by chance. And if you look at the model performance, so I looked at the interpolated model performance and the simulated ones. We can look at the histogram. These were 33 random simulations for the whole time period, and I calculated the Nash-Sutcliffe efficiency of the model, and you see it is quite varying depending on which realization was just randomly taken. But unfortunately, the interpolation was here. So this shows that this problem will not be solved by randomly searching among the precipitation fields. We need a different technique, and this different technique is that we try to do a simulation of these random precipitations where we condition it on both the precipitation and the discharge. Okay, and we would like to see, do we find such fields which are looking reasonable and match the discharge also. This, if you would look at it as an optimization problem, you can say okay, I'm changing it until it matches. So it could be an optimization problem which would have something like 10 million unknowns. Quite a nice problem. About 100,000 equality constraints. Equality constraints means the observed precipitation data. 4,000 structural constraints, that is the covariance functions, and 4,000 distributional constraints. You should not go much out of the range. This is the point where my PhD students disappeared. Okay, yeah, it looks bad. So we have to try to simplify this problem, to simplify in a reasonable way, and this is related to hydrological memory. We are in a very fortunate position in hydrology because the catchment is kind of forgetting. So it's quite good. I'm also forgetting many things, but the catchment does it in a regular way. So if you look here, you see here the discharge series as a black line. I took the discharge difference between day t+1 and day t, and this is the red line. And what you see here is that you have times where you have some kind of impulse, you have a disequilibrium, there is too much water coming in, then the discharge increases, after that it decreases, and so the difference is going into negative, and then it goes back to equilibrium. What does it mean? It means we are fortunate. We could say that the precipitation which goes this one will not have too much effect on this one, because in between it was already going into equilibrium. Okay, and that is good, because that means that if we try to modify here the precipitation fields, we can do that for these peaks individually, and look how is the model performing from between this and this peak. So this and this disequilibrium point, and we do not have to look at their joint effect, because there is no joint effect if they are far enough. So that is one point, and that means if we wanted to minimize, for example, the squared error, the squared difference between the model and the observation, so we wanted to have the precipitation values so that the model discharge is close to the observed discharge, we can separate it if these time steps are far enough from each other as individual optimization problems, many. And then we have many small optimization, smaller, not very small, but smaller optimization problems. And here for most catchments, 10 days were enough. After 10 days, it was not much memory left, so we could just go for that. And we could practically change our one big optimization problem or big inversion problem to many small ones. So this is the technical part. And then now let's look, how do we solve such a problem? So practically we want to find one precipitation event here at the beginning, so that changing that event until the next one, it looks good. Yeah. So that is what we want to do. So first we have to select the events, and we selected the events based on daily precipitation, and all days with precipitation above a threshold were considered in order to have this interaction, so interference problem. We selected on days which were at least 10 days apart. So the biggest precipitation event, which were 10 days apart. Of course, this is not necessarily enough. We then take a second set, which are of the rest, again 10 days apart, and the third set, which were also in 10 days apart. And then we optimized for the first, then subsequently for the second, then for the third, and then went back and forth through the whole thing. Totally 16% of the days were selected. This is, in fact, something which is nearly covering everything, because in 16% of the days you have more than 80% of the precipitation falling. So it doesn't really matter what happens on the rest of the days. On the rest of the days we take interpolated precipitation. Okay, so then practically we reduce the problem to 500 individual problems with approximately 2,000 unknown values, because each pixel has its own precipitation values. Only 30 equality constraints for each day, so for each case, and 30 structural constraints on the covariances. Each step, when we try to do the optimization, we use a model run. This is an expensive, very expensive experiment. One realization, that means about a certain number of steps until we get something what looks good, needs about 600 sheet runs, which is about 2,500 CPU hours, which is 4 months, if you would do it sequentially. But of course, nowadays you can work on clusters, and I used partly 300 CPUs at the same time, and that even tolerated that about 5 times I made a mistake in the code, and or I deleted the results. So all this nonsense was somehow covered, and I had solutions. But how were these solutions obtained? The methodology was, first we calculate a smooth field, the interpolation, and we drive the model with that. Then we apply a random perturbation on this interpolated field. We just modify it a little bit. And we define 2 different perturbations, and we somehow combine them both to a third one. And we try to find a good combination, and there's a Shannon-Whittaker algorithm on the circle with which this can be done very nicely. I will show something to that. And then we combine the individual optima for these 10 days, at least 10 days apart points. So, what is the essence here? The essential thing is we want to perturb a field. We are changing the precipitation. Okay, we are changing the precipitation with a modified field, which is 0 at all the observation locations, because we do not want to change the observations, and which has the correct variability, which is not something nonsense. And it's also very important, which I have not mentioned here, which also keeps us in the range, in the positive range. So we cannot generate negative precipitation. And what we do here is we do a trick here, which is a continuous perturbation. So we kind of slowly modify this field. And the interesting thing, if you can parameterize these slow changes in your field, then you can interpolate between them. What does it mean, interpolate? You are not interpolating the rainfall, but you are interpolating the discharge. So if I have a little bit modified field and another little bit modified field, the discharge for a field which is in between will be in between these two. So I don't have to run the model for that. So instead of running 360 models, I can run only 10 and do the rest with a kind of interpolation. It is not fully exact, but it's enough for me to select the best combination. Okay, so formally, of course, this is a scientific place. I should show equations because else you are not impressed here. What we do is we do a transformation of our original field, this is the rainfall field, back to a normal field. So sorry, this is the rainfall field. It's coming from a normal field. We are modifying the normal fields. That is assuring that we have the right distribution and that we always remain, of course, non-negative. The trick here is to keep the variance constant. We need for a perturbation field, we need that the sum of the weights, the squared sum of the weights is 1, not the sum of the weights. That's how cosine and sine are coming in here. And that means we can parameterize this with an angle between 0 and 360 degrees, with all of these degrees, all of them correspond to a field. Yes? And now we will run the model only at every 45 degrees, and in between we are interpolating. That is really the trick. And here you see some candidates. So you see that the candidates. This is when you go around with your phi, so with your angle. And you see that they are all similar because at the locations, at the observation locations, they have to honor the observations. But it's a continuously changing field because we wanted to use this wonderful possibility that we can interpolate between the performance of these fields. So this is what we do for one iteration for every day. It took me 1 day to produce this video because I'm not the right person to do these kind of things. So you should look at it for a longer time. These are our candidates, and we select the best among these. Once we have the best, we take that as an initial for the next. We apply a perturbation on this one, and we go like that until we are happy. Okay, and what happens? It's very interesting. Even 17 iterations. That's not too much. 17 iterations are enough to boost the Nash-Sutcliffe of 0.841 to 0.911. That is reduction of 1.7 million to 1.038. So I did not touch the model at all. I took the model as it was. And just by slightly modifying the precipitation, we have a much better model. And on the Neckar with 31 iterations, because it was smaller, the model was running faster, it was not such a big problem, we increased from 0.8 to 0.9. And practically, we have half of the squared error. That means it could be that the model is good, and there is a reasonable precipitation. We did not violate too much on the precipitation, and suddenly the model is good and much better as it was before. So there is no real contradiction here. And if you look, previously we have seen if we take randomly these realizations, they are very, very different. If we took it after this inversion exercise, for this time period, the dashed lines, you cannot really distinguish with them. They are very close, and they are very close here at the high things. This is not a realization, this is the interpolation, what we had. So we can get very close to this, and here we are not very close, because this is not the precipitation process. These are other processes what we did not touch. So this is where the model has to be improved, because this is not precipitation uncertainty. I wanted to see what can be explained with precipitation uncertainty. So that is what we got, and these are now the different iterations. So how the field is, the best fields are following each other. Once I had the program to make videos, I made a lot of them. So if you wish, we can look at all the 500 events as a little video. So practically, what we had here are optimizations, so kind of stochastic optimizations with reasonable precipitation fields, which then do a good discharge simulation. Here you see what was the interpolated precipitations for the time. Very smooth. And these are 7 of the realizations which could have been precipitation, which did the right discharge. And this is for one given day. And for each day we have, or each important day, we have such a big sequence. So you see, we still do not know how the precipitation in reality is, but we have a higher variability than this one. So this is important, and we have very different possible realizations. I have even more of these, but I could only fit 8 on the image. Okay, so the main difference is really the variability, and that was done. And you see they are similar because at the observation locations they are identical. Okay, now let's see what happens with the model. For example, if we take a peak over threshold method and we select the biggest 12 values, so practically 1 value per year, this red distribution is what the model would produce with interpolated precipitation. The blue one is what was measured. And the green one here in between is what we got after modifying the precipitation. So we can get reasonable extremes, and the reasonable extremes with the same model. So the model itself can produce reasonable extremes with reasonable precipitation, which is not smooth. Okay, so that is what we had here, and the next question is: do we have a better precipitation? Is this nonsense? Just producing nice colored pictures, or is it something what makes sense? What did we do? Of course, we cannot directly check this because we do not know. We do not know what the precipitation is. That's good for a modeler. Anytime when you have no data, your theory is not contradicted. What we did, we used a different hydrological model. We took the HPV, a spatially distributed HPV, exactly the same resolution as the previous model, as the sheet run, and we put the precipitation, what we optimized on the other, into this model, and wanted to see what happens. And in fact, we did not only do that, we took 4 different steps. Something at the beginning when it was not that good, then when it was improved and improved further and improved further, to see, do we get the same sequence in the other? And what really happened, we had the same kind of gradual improvement in the other model, which is a kind of proof that we are doing something which has something to do with nature. So, of course, the improvement was not the same for this model, but the better was better and the worse was worse, which is at least assuring. Okay. Of course, you can say, okay, but why are you playing with precipitation? Precipitation is not the only source of uncertainty. You can have discharge uncertainty, discharge measurements. Discharge measurements are much more friendly. They are more friendly if you have a good cross-section. Because then higher water level is higher discharge. You do not know how much discharge it is, but the monotonicity is kept. So you cannot do it completely freely. So practically you assume that your discharge is somehow a function of your water level and some kind of error term. And this error term is not a random error term. This is a function of the water level. And what you can do here is you try to find a new rating curve which is better for the model. I tried that, and practically if I use the best precipitation what I obtained previously, I could get another 10% out of this in the performance. Not in the discharge. In the discharge, the maximum change what we had here was something like 5-6%, and it was for low flows. So in the high flows, it was something like 2% what you had to change in your rating curve, and then it suddenly became better. So there are many ways to improve your model through the data. And the thing is, you do it in a realistic way. You are not inventing data, but you are trying to do something what could have happened. And the uncertainty is so high that this is fully acceptable. Okay, so that was the other. So in my opinion, we should not separate simply the uncertainties. What we often do is we give the observations to one person. You do the precipitation for us. You make the best precipitation estimation. The other does the discharge. The third is working on a model. And it's no surprise that it does not work. They have to harmonize in a relatively good way. And I looked at some. I was at a PhD examination in Sweden, in Uppsala, where the PhD candidate did a very negative work showing that global hydrological data are completely inconsistent. So precipitation plus potential evapotranspiration, discharge plus potential evapotranspiration is less than the precipitation, or discharge is more than precipitation in large regions over long times. And it is not a surprise because they were done completely decoupled from each other. And nature is not decoupling these things. So we have to think about this coupling. And what I did is not an exercise what you should do, but I just wanted to show you that one could go from the other way around and also have something reasonable. That means the good way would be to harmonize observations, model parameters, and output. And if you do not have contradictions, then it's a good thing. It's a reasonable model. If you have contradictions, then you have somewhere a problem. But it's good to know if you have a problem. And hydrology is strongly driven by variability, so you should take that into account and try to find models which do not contradict the data. That is our next goal. Okay, so I have a last slide. What I was showing that inverse modeling of hydrological models is also possible. Mild changes of precipitation improve the model performance for the two catchments which I have taken about 50%. It's a lot. Inverse models lead to better precipitation estimates, and even other models perform better. Interpolation will not solve the problem. Interpolation is doing something totally different. And the very simple example for that is the dice. What is the best estimate? The best estimate is 3.5. But you can never have 3.5. So it's something what does not happen, but you would put it into your model. And we could put it in a betting model, and nobody would bet 3.5. So this will not solve the problem. We have to do it in a different way. Maybe we should focus a little bit more on the observations and not only trying to change our models. Okay, the further applications of a similar technique are for extremes or radar are also possible. So the technique is not only for hydrological modeling, it's a general inverse modeling type of thing. So I think this is the end. Thank you very much for your attention, and I'm ready to take questions.
Okay, thanks very much. Some questions. Saman, maybe just use the mic.
Thank you very much, András, for the very stimulating talk. And I was inspired by your last conclusion or comment on the need for coupling the measurement of precipitation, streamflow, and modeling efforts. That's a very great point. I think the problem that you're talking about is exactly the problem that we are dealing with in Canada, which is we have a very sparse precipitation gauging network in Canada, and then we end up interpolating our data, and we already know that we get a lot of uncertainty in precipitation. So I think there is definitely a lot of potential for applying these kind of techniques in Canadian landscape. And when you were presenting, I mean, I had a question in mind, but you then later nicely answered it. But I still want to pose the question. So when we fix the precipitation domain stochastically, the way you did, we are making an assumption, an implicit assumption, which might be quite strong, that the model is right, or the model is a good representation of what is out there. And then we base everything on that, and we do reverse hydrology or backward hydrology, and we try to fix precipitation. Of course, when you showed that you used other models later to see, okay, if you assume the first model.
The Sheetran.
Yeah, Sheetran, for example, you assume that's the correct representation and you fix precipitation, and now let's use HBV instead. I mean, that could be some sort of validation for that, but probably still not quite enough to look at that. So that was basically the thing that crossed my mind. And the other thing that I didn't get was how you looked at covariance structure of the precipitation domain in this. Yeah.
Yes. First of all, this is an extreme example. I wanted to show you the reverse of what people are normally doing. And at the end, I try to stress you should also take care of your model. But I wanted to show that without even touching the model, you can improve. Of course, I don't believe that the model is perfect, but we would have to quantify something what we expect from the model as quality. The generation is done here in a very simple way. Practically, our field, what goes into the model at the end, is this here. Yes, this is the interpolated field, which remains the same for every step. And this is a randomly generated field with the right covariance model. And 0 at all the observation locations. This is normal geostatistics, you can get that. And this is another one. So these are two, and they are, if you take a combination where the squared sum of the weights is 1, then you keep the covariance. Then the covariance does not change, and that's a big advantage, because then you can do this trick on the circle and interpolate. Okay, and this is we do a spectral simulation, but there are people who are doing it with other methods.
Other comments, questions? Yeah, the back. Sure, Van, I don't know if you have a mic. Oh, there you go.
Thank you very much. I have a question regarding evaporation.
Yeah.
So I didn't see anywhere in your presentation about the evaporation, and that's the important flux, because that's where you kind of can fit things.
Yes, yes.
Yeah.
I assumed that is also okay. We could, of course, invert on that also. In fact, what my personal feeling with these models is that there we need a different time scale. For discharge simulation, it doesn't matter what was the hourly evapotranspiration, but the hourly rainfall might matter. So practically there we could invert over weeks or a few days. So it depends always on the scale. And we have to, the only thing is to find the right blend. And of course, I did not find the right blend, because I did not even want to find the right blend. I wanted to provoke you that this is possible, to assume that everything is correct.
Well, we can. I have questions, but maybe we can keep it for later.
One down the front, Mark, and then at the back. Thanks. John.
Yeah, András, how much was the hydrological model conditioned by the original precipitation errors, which must exist? Particularly if it's HPV, the evaporation would be tuned to those precip quantities.
What do you mean? I did not really understand the beginning.
Okay, the evapotranspiration, the actual evapotranspiration, in a model like HPV and also in SHE, SHE uses a coefficient as well. It's neither has a physically based approach to that.
Yes.
Yeah, that's going to be the difference. Neglecting storage over a long time.
Yes.
Between your precipitation and your discharge.
Yeah.
That you're conditioning here. So how much was that set by the original precip field and errors within it?
In fact, if you look at the Tyne, Tyne is not the place where you would go as a tourist, because it's raining too often. That means you have ETA equals ETP.
I would also argue that there's a lot of, because of the high frequency of rainfall, that intercepted rain evaporations can be very high from any vegetation, things like that.
Yes,
so.
but it's cold. Mm-hmm. It's relatively cold. It's not a very pleasant climate. In the Neckar, we also have practically more energy limited than water limited conditions. I did not. I was driving both models with exactly the same evapotranspiration, and I took the evapotranspiration exactly the way which I was criticizing. I took the evapotranspiration from the UK Met Office, which was produced by the former Institute of Hydrology in a gridded basis, and I did as if I would believe that.
Okay, yeah. No, an evapotranspiration scientist would take the precip and the discharge and believe them, and then try to upscale an eddy correlation or something like that. But there's still errors in all these things, and it's tough.
Absolutely agree. Everything is uncertain, but there are limits. There are limits of credibility. If I would need for my model 1,200 millimeters evapotranspiration in Saskatchewan, then everybody would say that this is nonsense.
Yeah. The just one other aspect, the Environment Canada, as it's developing its flood flow forecasting system, part of the interest that the meteorologists have in this is finding a way to use stream flow information to see how well the atmospheric model is doing at precipitation.
Yes.
Which is
Yes.
kind of interesting.
Yes.
And because we have better coverage from stream gauges if we look at the basin than we do precip gauges in many parts of the country. So
Yes, but that is also an inverse problem.
exactly.
Yes.
That's the meteorological interest in discharge, which is interesting. So it's,
Yes.
thank you.
As we go to the next question at the back here, as a field hydrologist thinking about this discussion, when I think about your Comet Halley setup at the beginning, that physics, and Cobb can correct me if I'm wrong as a proper physicist, that physics seems quite linear, whereas our catchment systems are highly nonlinear, with these characteristic forms of nonlinearity like thresholds, feedbacks, hysteresis. So when I listen to this discussion and I see what you're doing, I'm wondering if you've applied it to the subsurface. I mean, we have radar rainfall. We have had Vitek Krajewski here a few weeks ago talking about products to characterize what we can observe, but a lot of the nonlinearities come from what we can't observe, how storage is spread over the landscape, and how even if you had the perfect model, the perfect rainfall field, if you don't know that storage distribution, man, you're not going to get those characteristic forms of nonlinearity. And that's what makes us so much more difficult than predicting when Comet Halley is going to come. So I just wonder if you could comment briefly on that, because that seems to be our, this frontier beneath our feet, as Bill Dietrich would say, is really what we ultimately have to come to grips with.
That's a very interesting thing, because you can learn with time. If you are interested in soil thickness for your storage, that is a different thing. There you have chance, because if you observe for a long time, after a certain time, certain possibilities will drop out as impossible. And there you can invert on that, and there you are in a little bit similar situation as with the discharge. You cannot have a different soil depths on day A and day B.
Yeah.
But you have a different rainfall. So rainfall inversion is in this sense something which will always be a problem. But we can, to some extent, do that with.
Unless you can measure it,
we
I guess.
did quite a lot of inverse modeling with the same technique for groundwater modeling.
Right. Was there another question back here? Yeah.
Just had a comment on the original field. You also, I don't know, maybe put a lot of trust on the gauging stations originally, so that it all had to fit on there. I remember in the Calgary flood here in 2013, the models were not getting it because the precipitation fell in between the gauges, where we didn't have the information. In the maps you showed, I saw some blue areas coming out, like there is some additional precipitation coming that were not captured by the gauges. So I don't. Is the system able to produce?
Yes,
that?
The system can produce rainfall, higher rainfall, of course, than the interpolated rainfall, and higher rainfall a little bit higher than the highest observed. It can. So it is your inversion what decides on that. So here you see that we have some candidates of heavy precipitation in this region. No, sorry, that's low precipitation. So it's a relatively dry thing, and the maximum can here grow and or decrease, and that's all possible.
Okay, I'm sensitive to time. One last very quick question, and then we're going to draw to a close and encourage everyone to go out and drink coffee and eat cookies and continue discussions.
Hi, thank you. That was excellent conversation, excellent talk. I'm just wondering, do you think this is an approach that could be used in a forecasting context?
Yes, it could be used in a forecasting context. in a kind of way that you try to find out what happened in parts of your catchment, because not everything was already producing a discharge. Some of your precipitation until now is important for your future. So in this sense, it could be used, and I see many possibilities for the applications of this. And you could not only condition it on the point observations, but also on a radar image. And then you can continue the radar film with some techniques and get maybe a somewhat better.
Good. Well, on that hopeful note, I'll draw things to a close. And join me, please, in thanking András for a great talk. Thank you.